first step that we took towards starting our project was the project management and project scheduling phase. To do this, we had to clearly define a timeline as well as assign tasks towards specific timestamps and dates. To do this, we used various charts such as WBS charts, Gantt charts, communication matrices, and quality acceptance criteria tables. The second step that we used to further our progress was to clearly outline our roles and responsibilities. To do this, we used a modified RACI responsibility matrix that used pictograms instead of the standard alphabet system. The second thing that we did was split our team into two separate departments. The first one is the enterprise department and the second is the engineering department. The enterprise department consists of the head of enterprise, financial manager, head of graphic design, and head of marketing. The third step was to evaluate our financial resources and assign a budget. To do this, we used two main techniques. The first one was parametric estimation and the second was three-point parameter estimation. We mainly used the three-point parameter estimation in which we had an optimistic scenario, a most likely scenario, and the worst case scenario. Three-point estimation was more accurate than parametric estimation because it placed more weightage on the most likely scenario instead of the most optimistic and the most pessimistic. The formula that we used was O plus 4M plus B divided by 6.
A major contributor to success was sponsorship. Sponsorship provided the resources and support needed to design, manufacture, and test assemblies in cars. To attract partners, we created bronze, silver, and gold sponsorship packages, each offering different levels of brand visibility through a card, uniforms, portfolio, social media, and outreach activities. We approached sponsors whose values aligned with innovation and education, and in return provided meaningful exposure to workshops, community engagement, and digital campaigns. We measured the effectiveness of these partnerships using return on investment ROI, return on objectives ROO, and return on engagement ROE, ensuring value for both our team and our sponsors. In the spirit of sustainability, our team participated in EEG campaigns to promote environmental awareness and responsible practices within our community. Through these initiatives, we demonstrated a commitment to making a positive impact beyond STEM racing.
Marketing and digital media played a key role in building a Stratospeed brand and increasing our visibility. We targeted students, STEM enthusiasts, industry professionals, and potential sponsors through activities such as CAD workshops, branded merchandise, and community engagement. To attract sponsors, we used Instagram and WhatsApp, sharing team updates, engineering progress, and sponsorship opportunities. We also applied SEO to improve our online visibility and used content targeting to create relevant content for different audience groups. Through our omni-channel marketing approach, we maintain a consistent and professional brand image across all platforms. Digital media helped expand our reach with Instagram driving engagement, LinkedIn connecting us with professionals, and YouTube showcasing our project journey and achievements. Together, these efforts strengthened the Stratospeed brand, increasing audience engagement and provided valuable exposure for our sponsors.
We analyzed all the physics concepts affecting our car. Our three main objectives were race performance, durability, and compliance with STEM racing regulations. We investigated the key aerodynamic forces acting on our car, specifically thrust efficiency, inertia, tipping moment, launch efficiency, and aerodynamic efficiency, including adverse pressure gradients, wheel weight, and the Magnus effect. Understanding these forces weren't just theory. Every design decision we made in CAD came back to this research. If a shape created drag or disrupted airflow, we had the science to justify changing it. One of the first things we tackled was the wheel design because wheels are more complicated than they look. When a wheel spills up from a standing start, it needs energy to start moving, and the further mass is from the center of the wheel, the more energy it takes. So getting the wheel geometry right was really important for acceleration. We modeled 3 different wheel designs in Fusion 360. The first was a 3-spoke wheel. It looked fine, but when I ran structural analysis on it, the large gaps between spokes meant parts of the wheel were flexing too much at speed. It didn't pass our criteria, so we moved on. The second was a 5-spoke wheel. More spokes meant better support across the wheel. Less flex, less energy loss to the wheel deforming as it spins. This one hits the balance we were looking for. The third was a 7-spoke wheel. We tested it to see if more spokes meant better performance. Structurally, yes, but the extra material added weight which actually worked against us by increasing the energy needed to accelerate the wheel. The gains didn't outweigh the cost, so we went with the 5-spoke design, best balance between stiffness and efficiency. We also selected 3 into 8 into 3 mm hybrid ceramic bearings.
Ceramic has a very low friction coefficient, handles heat well, and the small size keeps friction centralized, which all adds up to less energy wasted. Prototype A started as a hand sketch, then became an early CAD model. From a design standpoint, I could already see potential problems. The nose was too wide, and the surface transitions between panels were quite sharp. My concern was that the air would struggle to follow the body cleanly.
And the CFD confirmed it was the worst result out of the three. The front wing was practically non-existent and the car had no downforce because of that. The center of the mass was also concentrated near the canister hold because the front wing wasn't adding the weight required near the front of the car to balance it out, which meant when the car would reach top speeds, it would spin. The wheel wake was also extremely wide. It dominated the entire front half of the car. The side pod inlets had fully separated recirculating air, which increased drag by a lot. The drag coefficient of the car was 0.712, which is far from our target of 0.4.
So, for prototype B, we made two key changes. First, we narrowed the nose profile, the idea being to guide air smoothly around the chassis rather than letting it pile up and spill sideways. Second, we added fluid transitions between surfaces, smooth curves instead of sharp corners, especially around the air cartridge chamber and the wing mounts where airflow is most sensitive.
With this design, the yaw moment issue was finally solved as the front wing added the necessary weight to the front of the body, balancing the center of mass. The mid-body had less tread, some attached flow was finally being visible, but the wheel wake was still responsible for the majority of the drag. The front wing was also creating a lot of downforce that was creating drag. The side pods were trapping air on the underside and contributing to drag as well. So in the next iteration, we plan to change the front wing to reduce the downforce and to change the side pods so less air was being trapped on the underside of the side pods. The drag coefficient of the car is 0.542.
The final car addressed those issues. We enclosed the side pods fully, dropped the ride height, and made sure the body tapered smoothly from front to back. The front wing also went through its own iterations. Version 1 had open tips which are generating vortices at the edges where high pressure air was spilling around. Version 2 added vertical end planes to contain that airflow, which cut the vortex problem significantly.
This is our final design. The front wing was optimized to reduce the drag while still keeping sufficient downforce and balancing the center of mass. The wheel wake was reduced sufficiently and the flow was staying attached to the body, which meant reduced friction drag. The underfloor was also sealed properly and the side pods were narrowed to reduce the air being trapped inside, which further reduced drag. The drag coefficient of this car is 0.401.
Once the design was finalized, I took it through to physical production. The car body was CNC milled. Once it came off the machine, I removed the support material and began surface preparation, starting with a 360 grit sandpaper and working up to 400 grit. This removed the scalloping and surface defects left by the milling process and brought the car dimensionally closer to the CAD model. Before gluing anything, we did a full dry run assembly, fitting all the parts together with an adhesive first to check fit and alignment, especially around the wheel support structures. Once we were happy with the fit, we bonded everything with 5-minute epoxy. For finishing, we applied 3 coats of primer to each car with a light 400 grit sand between each coat to dry. For sponsor placement, we used vinyl decals. We initially considered water slide decals, but the vinyl was a stronger choice. Water slide decals are fragile, prone to tearing during application, and can lift or bubble under clear coat. Vinyl is more durable, sits flat on the surface, and bonds more reliably, which gives a cleaner finish and holds up better through the clear coat process. Once the decals were applied, we finished with 1 to 3 coats of clear coat to lock everything in and give the car a gloss finish. Additional clear coats were added until the car reached its satisfactory weight. Throughout the process, we ran a full risk assessment before beginning any work. All spray painting was done outdoors with PPE, including dust masks. When using tools by hand, the workpiece was always secured and fingers kept clear of cutting parts. We also consulted safety data sheets for materials like primer and paint to understand the hazards and first aid procedures.